The other parameters, I'm not going to spend too much time, beta and gamma. Those beta and gamma really are related to how this shape looks like, whether it is like more like an S shape or more like an linear shape. So by changing alpha and delta, this shape, whether this becomes like this, like an S, or more like a linear type. That's what these are. Okay, now we were talking about shift factor. Now here you can see we were talking about shift factor. This is what I was talking about. So I'm gonna turn on this document camera again. So reduced frequency. We said reduced frequency is f times a of t. This is the shift factor, this is the frequency. If you take the log of both sides, this is the same thing as log of fr is equal to log of f plus a log of f or a of t. So log of f plus log of a of t, this is the same thing. Mathematically, these are the same things. So fr is 1 divided by tr. F is 1 divided by time. And a of t is the same. This is how it is. So in other words, reduced time is time divided by a of t. Okay, we go from here and from here. If you take the log of both sides, log of tr is equal to log of t minus, because it's the denominator, log of a of t. So that's what the difference between shifting in time and shifting in frequency. You're really subtracting this component in log scale, and you're adding this component in log scale in frequency space. So that's the only difference between those two. So in the dynamic modulus master curve, so if this is E star, let's say, this is the frequency, that is reduced frequency. This is the reduced time. We're talking about the log of the reduced time, log of fr. The shape looks like this. And in terms of time shape, it's like a mirror image of this essentially. That's the difference between, and this is in time, and this is in frequency space. Okay, essentially the same, except this is like a mirror image.
You sure you don't want to integrate something for the group? Come on, give them a little bit of that.
Sure, okay, let's do that. Convolution integral. Stress, I will do it, is equal to convolution E t minus tau dE d tau. And I'll tell you about this later on. My colleague Karim Chati, he'll probably hear this. He says, when I see that integral, I feel like nausea. Okay. We do use that integral, by the way, to the true viscoelastic solutions of moving load. We use that integral to solve for actual stresses at different times, but I'm not going to get in there. So, because if I get in there, by the time I'm done, I might be the only one in the room. All right.
None of us will have the air left.
All right, so All right, so that was the reduced time minus the logarithm of shift. That's the reduced time. Now you can see as a function of temperature, shift factor, that A of t is plotted. This is also an output of the pavement ME. So when you see these two, that's what it means. This is a shift factor. So it means that if you look at this number is about 4.8 or so, 4.8. That corresponds to 14 Fahrenheit. That means that if you look at this temperature, this number means that all these data points moved to the left by 4. That's what it is, 4.8. Everything if you move it back by 4, that's where the original time was. So that's what it means. So this means that from here to here is 4 seconds. For this one, from here to here is not 4 seconds, 10 to the 4 seconds actually, because in logarithmic, it's 10 to the 4 seconds. This is 10 to the 2 seconds, 100 seconds. This is 1, no shift. And this is plus 100, and 0.002, actually 1/10, and so on. Now, how do we get the shift factor? Now, pavement ME uses a special technique. So normally, in normal circumstances, you don't really need any other data to shift. You go to your lab data, you start shifting manually, and then you come up with the surf. You don't need that. But pavement ME does in a different way to simplify, I believe, to simplify the shift factor equation. You can see the shift factor equation is a little bit simpler. It's a C times logarithm of the viscosity of the binder here, time minus the logarithm of the viscosity at reference temperature, So from the input of all bunch of G stars that you input, it converts the G star to viscosity using this relationship. G star divided by 10 times 1 over sine delta to the power 4.8628 is the relationship converting viscosity to the G star. Now, this equation is somewhat empirical, because normally, theoretically, for linear like a pure fluids, linear viscoelastic fluids, pure fluids, this component doesn't exist. This is only G star divided by the frequency of testing. This is 10 because we run the test 10 at 10 radians per second. But some binders are nonlinear in nature, and because of that, this was a better relationship that they come up with. So when we run a test, and when we input that into pavement ME, G star is a whole bunch of G stars at phase angles. They are converted to N viscosity at different temperatures, because we have the G stars and phase angles at different temperatures. And then we have this relationship to come up with the log AT. And then we will do, we use this log AT to shift the curves. And then we use the shifted time to find the best fit line. Also, another output you will see from the pavement ME is this, what we call AVTS relationship. We talked about it a little bit yesterday. So what it says is log of viscosity, log of viscosity is equal to A0 plus VTS 0, and this is kind of incomplete actually. It's that must be a typo there in the output. Just in any of the versions, do you see AVTS times temperature here, or never, right? Do you remember there's a typo here in pavement ME output? You don't recall? Okay. So there's always a typo. Unfortunately, they haven't fixed it yet. But if you look at the actual equation, they were trying to put this in here. But so actual equation is this: log of the viscosity is equal to A plus VTS, which is like the slope, times the logarithm of temperature. So that's missing here in the output of pavement ME. Again, so this log viscosity is coming from the G star.